But energy isn't limited to just the world around you. It can be found anywhere in the universe. The main source of energy used on our planet is the sun. The sun is a vital resource for all organisms, but it can also cause a lot of harm if you're not careful. The sun emits a lot of ultraviolet radiation that can harm the skin and may even lead to skin cancer through overexposure. There are many types of radiation energy that are emitted from our very own sun. Speaking of the sun, to keep yourself protected is extremely important to your health. One easy way to keep yourself safe from the dangerous ultraviolet rays of the sun is by using sunscreen. Thanks. Sunscreen creates a layer around your skin that helps absorb and reflect those rays. Sunscreen come in a variety of different SPFs or sun protection factors. Different SPFs offer different levels of protection from the sun. The number is determined experimentally indoors by exposing human subjects to a light spectrum meant to mimic noontime sun. If your skin would normally burn in 10 minutes, applying 15 SPF sunscreen would theoretically allow you to last in the sun for 150 minutes, or 15 times longer than your skin would regularly burn. Sunscreens come in a variety of different forms. Some are just regular bottles and others come in a spray type.
Hi, I'm Dr. Connor Shimoto, and I know a lot about potential energy. There are lots of forms of energy. Some can be harmful. That's why I invented Shimoto UV sunscreen protection. Has this ever happened to you?
I can't wait to give these people skin cancer with my harmful UV rays.
Oh Lord, it's so hot out here. It feels like I'm getting slipped by the sun. Oh my goodness! No, the sun! No! The sun is too strong!
You should have known that I had harmful UV rays. You should have worn sunscreen.
No! Son, you're eating all these chips. You're not using any of your energy. You gotta go outside and do something.
No, Papa, you don't understand. Just by sitting here and eating, I'm using all my energy.
Is that what this Mr. Chang guy's teaching you in class? Because I think you should go use your energy outside right now. I mean right now. Get out there. Right now. Yeah. Son, wait. You gotta be careful out there. There's dangerous UV rays from the sun. Gotta use your sunscreen.
Thanks, Papa.
I got you, son. Don't worry.
Man, the weather's so nice out today.
Why aren't you getting hurt?
Joke's on you, I have the proper protection.
Oh darn it, my plan didn't work.
This is why I invented UV Shimoto protector, so when your mean old man kicks you out of the house, you can have a safe and fun time.
Absorption is when light reaches a surface or an object that can absorb all or portions of the light. Darker colors absorb light more readily than lighter colors, which is why when you wear a black colored shirt on a hot summer day, you tend to feel hot because the light from the sun is being absorbed in the dark material in your shirt, which is transferred into heat energy. Reflection is when light reaches an object and it bounces or is reflected partially or totally from this object. There are two types of reflections: specular reflection, also known as direct reflection, and diffuse reflection. Direct reflections are when light is reflected off of a smooth surface such as a body of water or glass, and diffuse reflection is when light is reflected on rough surfaces such as shattered glass or asphalt. Now for our first demo, we're going to show you how UV rays behave when interfered by sunscreen. UV or ultraviolet rays can easily penetrate through your skin and other surfaces, so by applying sunscreen we can essentially deflect the UV rays from the surface. That's why here in this demo, we will see a significant difference in the areas covered by sunscreen and in those areas not covered by sunscreen. UV rays are stronger than violet light and cannot be seen with the naked eye. Electromagnetic radiation in this range of wavelengths is called visible light or simply light. Here we can see that it is almost impossible to see the sunscreen on the white shirt, but once we put the shirt under the UV light, it appears much more visible. This is a reflection of the UV light that is being shined right above it. On the molecular level, let's say the sun releases about 100 photons. Without sunscreen, all 100 photons will be exposed to the skin. But if we use sunscreen, then less photons are available to penetrate. To be specific, only about 7 out of 100 photons make it through. An analogy to remember the way of the light spectrum is relating it to a piano. As you can see, the left side of the diagram indicates it has a higher frequency and has more energy, just like the left side of a piano where the sound lasts very quickly. But if you look at the right side of the spectrum, the wavelength increases and so does the duration of sound of the keys on the right side of a piano. Also, you can see the UV rays are more towards the left side of the spectrum, indicating that they have a good amount of energy.
We all need protection from the sun's ultraviolet radiation, also known simply as UV radiation. It includes both UVA and UVB wavelengths. UVB is a common suspect for sunburns and short-term effects, whereas UVA rays are known to cause more long-term effects such as wrinkles and other long-term skin damage. But contrary to popular belief, both rays can cause skin cancer in the long run. So, how does sunscreen work? Let's think of our sunscreen as a beach umbrella. No sunscreen completely blocks all UV rays, but by using the right product and taking the right skin protective measures, you can decrease your risk of skin cancer and other harmful effects of the sun. To adequately protect you from these rays, sunscreen should have a sun protective factor of at least 15. But this isn't completely enough. It may block some UVB rays, but it won't stop all UVA rays. Now, by using sunscreen that indicates its broad spectrum coverage, you can be protected by both UVA and UVB rays. Broad spectrum sunscreen is usually composed of octanoxate, which absorbs UVA rays, and avobenzone, which sucks up UVB. When UVA and UVB rays hit either molecules, their electrons get excited. When the electrons settle down and return to their regular energy levels, they give off relatively harmless amounts of energy in the form of heat. Now, if we increase the SPF but take out broad spectrum, we will have more protection for UVB rays, but less protection from UVA rays. In the end, it all comes down to having not only a SPF of at least 15, but a sunscreen that is labeled broad spectrum as well for maximum protection from the sun.
For going further demo, we performed a calorimetry experiment using these nuts.
These nuts? Got him!
We burned the peanuts until all of the energy was released into the water, and we can be sure that all of the energy was released into the water because of the law of conservation of energy. This law states that no energy is created, nor is any energy lost. It is only transferred. We can use calorimetry to find the energy that is being given off by the chemical reaction by using MC delta T. This gives us the number of kilojoules released from the peanut, which can then be converted into kilocalories by dividing by 4.184, and then converted into calories that we see on the back of a cereal box by dividing by 1,000. The equation for calculating calorimetry is Q equals M times C times delta T. Q represents the total amount of heat being transferred in the reaction. M is the mass of solution being heated. C is specific heat, which is the total number of joules needed to heat 1 unit of mass of that substance by 1 Celsius. And delta T is calculated by subtracting the final temperature by the initial temperature, or T2 minus T1. In our reaction, we had 50 milliliters of H2O, which represents M in our equation, and we had 4.184 as the specific of water, times delta T, which is 47.9 minus 21.1. When you multiply all that out, you get Q equals 5,606.56 kilojoules. To convert those kilojoules into kilocalories, you need to divide by 4.184, which gives you an answer of 1,340 kilocalories, which you need to divide by another 1,000 to reach calories.
Now for our final demo, we're going to be showing a very simple and easy endothermic reaction that takes place just by adding citric acid, baking soda with water. First, we get 10 grams of citric acid and 10 grams of baking soda into a large plastic bag. Then, we put the 30 milliliters of water into a smaller plastic bag. Now what we do is we place the smaller plastic bag into the large one, and what we're going to do is open the small one while it's still inside the large one.
20 minutes later.
Okay, now finally we are able to allow the water to make contact with the baking soda citric acid mixture. As you can see, when we add these three things together, there's a reaction along with the formation of carbon dioxide gas, excess water, and a chemical known as sodium citrate. And without the water in this reaction, the reaction simply wouldn't be able to take place due to the water being a catalyst. But the important thing here is to notice that this is an endothermic reaction. As you might be able to tell, the bag has cooled down and Arya simply refuses to observe this chemical reaction firsthand. Now, we're going to be talking about potential energy diagrams. I'm going to go through and label each part of the diagram to help explain a little bit about what they are. Now, down here, we're going to have the x-axis labeled as the reaction process, which occurs gradually over time. And up top on the y-axis, we're going to have the value for potential energy. And first, we're going to draw our little roller coaster of energy, which starts at one point, goes up to a point, and drops down to another point. Here on the left side with reactants, and at the peak, we're going to have the activated complex, which is where the reactants are just ready to undergo the reaction, but haven't quite really gone that far. The energy that is needed to get to that point, or the height of the hill, is known as the activation energy, or the amount of energy needed to reach the activation complex. Once that reaction proceeds, and we actually create our product down here, we can then identify the changes in energy that have occurred. The difference between the energy of the reactant and the energy of the product is referred to as your delta H value, enthalpy, or heat of reaction. If your value here is negative, then that's going to indicate that an exothermic reaction has occurred, and whereas if your value is positive, then it's going to indicate that an endothermic reaction has occurred.
A lot of harm if you're not careful. Sunscreens come in a variety of different SPFs for some protection factors. Light spectrum meant to mimic noontime sun. Some subjects wear sunscreen and others do not.
I can't wait to give these people.
No, stop! The sun! No!
And go!
I'm Dr. Connor Shimoto and I know a lot about potential energy. Today we will be cooking with these nuts.
What, you want to
Light the fire.
No, dude, now I gotta edit all this. Come on, man.
Hey, it was recording.
Oh my god. Yeah, he knew that. Okay. We're starting over.
Be in the video, like put out the fire. Like make sure your face is showing. Like go in. Okay, yeah, good. Just like pretend you're observing. Turn the lights off now.
Enery.
Enery.